So good morning, everyone. We will start our lecture for today. So we'll start with a review of some of the ideas that we have discussed in the last lecture, and we will go from there. The first important idea is, given a processor, we would like to, given a computing system, so there are two important things that we need to know about that computing system if you want to get some performance out of it. The first one is the raw compute power. How much, what is the raw compute power that is provided by the system? So that is the first thing. Yeah. So the raw compute power that is provided by the system is the first thing we need to compute, especially when we are going for performance. What is the overall compute power? What is the raw compute power that is available? And the second important thing is, where is this? What is the available bandwidth? What is the peak available memory bandwidth? So two ideas. One is peak gigaflops or raw compute power. So available peak. So here you have to be careful. So here we may want to use something like this, gigaflops per second. Okay. And so this is the raw compute power. Second is the memory bandwidth. What is the available memory bandwidth? So these are the two important properties or specifications of your system that you need to get. And this is measured in gigabytes per second, or yeah. So this is measured in gigabytes per second. So these two are the properties of the system. And then on the other hand, your program itself has the program that you want to, whose performance you would like to improve. You would like to you want to understand its properties. And an important thing about it is what is called as an operational intensity of the program. Operational intensity. So this is a property of the program, and this is a property of the system. These two are properties of the system. So operational intensity is measured in operations per byte of data. So operations per byte of memory fetched. So this is the property of the program. And using these two, we do what is called as a roofline analysis. That's what we will see in today's class to some extent. So we do what is called as a roofline analysis. And this roofline analysis will tell us what is where you should focus on in your program, whether you should, whether compute is the bottleneck, whether memory is the bottleneck, what is the bottleneck in your in the overall goal, that is you would like to improve the program performance, where is the bottleneck, it tells us. And while computing, just to recall, while computing the peak, the raw compute power. The raw compute power is given by the number of sockets on your motherboard into the number of cores per socket and the cycles per socket into flops per, cycles per second into flops per cycle, number of floating point operations per cycle. So on my system, so there is only one socket. But there are 6 cores on it. There are 6 cores. And the CPU frequency, baseline CPU frequency is 3.2 gigahertz. And it can go up to 4.6, and the cycles per second. 1 gig is equal to 10 power 9 cycles per second. So 3.2 gig means 3.2 into 10 power 9 cycles per second. And the floating point operations per cycle, I'm taking it as 8. I don't have a actual basis for it, but I am guessing it could be somewhere around it. So why I made that guess, maybe I will explain you in a bit. And then overall, this gives you this particular line. This gives you the flops count. And in order to get gigaflops, in the next line, we divide it by 10 power 9. So that gives us gigaflops. So for this program, for my machine, this is for my machine, the raw compute power that is available per core is 25 gigaflops or 26 gigaflops. But if I consider all the 6 cores, then the available compute power will be 6 into 25, which will come to around 150 gigaflops, 150, 160 gigaflops is where we land up. Well, this is the raw compute power, but then we have seen that it is not possible for us to extract this raw compute power completely because of various challenges, various kinds of issues that we face in the programs. So we try to see what is the, through programs, we try to measure what is the available, how much gigaflops per second we can achieve. And there are various kind of benchmark programs. And there is a benchmark, so BLAS, which is the assignment which you will be working on, a subset of BLAS programs is what you will be working on. And so there are different implementations of BLAS. Like for example, so there are different implementations of BLAS. So like for example, BLIS is one implementation. Open BLAS is another implementation. Intel MKL, Math Kernel Library, is another implementation. So there are different implementations of this BLAS programs, and usually they are very compute intensive. And if you look at the top 500 supercomputers, how much performance they are giving, in order to measure that, we use these programs, BLAS programs. These are called as dense linear algebra programs, dense linear algebra. And then there is also, we have what is also called as, we have set of problems for sparse linear algebra, because in many computer Okay. So back to business. So what we were looking at, so just want to check again. If, can you hear me remotely? Those of you who are there, you put a chat message. Okay, great. So what we were talking about is, well, in order to compare, so in order to understand, in order to actually see how much of raw compute power we can actually extract from a machine, we have dense linear algebra benchmark programs. So compare this with the sparse LA problems, LA benchmarks. And also, so as this only tells about the floating point operations that we can achieve, but there are many applications where, like for example, in bioinformatics or in high frequency trading, we may not do the computations could be on strings or or on integers. So these benchmarks are not representative for other kinds of workloads. And in order to understand how your system performs on those workloads, let's say you are buying a system to do certain kind of jobs, then you have to see how your system gives performance on benchmarks which are representative of the workloads that you expect to run on them. So please keep that in mind. The second is the available. So again, if that memory bandwidth, if you see here, this available memory bandwidth is this number. I got it from the Intel website. So assuming 2 channels and few things. But then again, we have to use some kind of benchmark programs to figure out what is the actual available bandwidth that you can extract. And in the last class, we have looked at what is a stream benchmark program, using which you are able to estimate that that we are able to get around 25 to 30 gigabytes per second on the machine. Okay, so these 2 points are important. Now, the second, so now let me share. We would like to do one important baseline thing. We'll see. Okay. So here we have the raw compute power, and so let's. So raw compute power, let's say we represent it as a C. So let's say it is something like some 25 gigaflops per second. This is what we have, and memory bandwidth is 40 gigabytes per second. And if you see for a program, we were looking at this program AX plus what is this program? Alpha times A plus both are vectors, right? Alpha X plus Y. Okay, let's use this. What is the operational intensity of this program? So Y is equal to alpha times vector X plus Y. Okay, this is the one. So how many computations are there? So there is one multiplication, one addition. And it's a vector. So there are, if this is if vector length is n, if you assume vector length as n, then the total number of operations will be 2 times n, right? 2n. Okay. And the amount of data that we need to bring from the memory we can assume that the scalar alpha is present in a register, so we don't need to fetch it from the memory. And if you assume if it is x and y are floating point, the elements of x and y are floating point numbers, then we have to bring in 8 bytes of data. So the operational intensity OI is equal to 1 over. The operational intensity is 1 over. Assuming this is for floating point, single precision floating point. And the same operational intensity, if you look for double precision numbers, then it will be 2n divided by 16n. So it will be 1 over 8. So this is the operational intensity. So the achievable, so for this program, for this particular program, what is the achievable so what is the peak achievable compute is operational intensity into compute power. Operational intensity into compute power. So the peak achievable for this program, if you see, let's go here. So for the program, this program is called as a AXPY program. For this program, the peak achievable thing is so for every byte of data that you fetch, you are able to do 1 over 4 computations are required. So the peak achievable flops is equal to operational intensity into compute power, okay, or into memory bandwidth. No, it is into memory bandwidth. Into M. So what happens is, so we will be able to get, if you assume memory bandwidth as 40 gigabytes per second, then what we will be able to get is we will be able to get 10 gigaflops per second. Okay. Does this make sense? This is what we were seeing here, right? So let's share. If you go, so peak compute throughput is operational intensity into memory bandwidth. So this is what we got last time actually. Control Shift this. So now there is a very important observation that I would like you to make. So on one hand, you can see here you are. So is your program, is this particular program, are we able to saturate the available compute power on your system? Does it make sense for you actually to use multiple cores? Does it make sense for you to use multiple cores? Because as it is right now, but on one side, if you see, one core can do 25 gigaflops per second. No, but you are not able to supply data at that speed. Okay, you're not able to supply data at that speed to even saturate the compute power of one core. Then if you go even for multiple cores, you may not achieve, there is a lot of compute power already available, but you're not able to provide the data to be able to process it at that speed. Okay. So what is the bottleneck here? Is memory is the bottleneck? Is compute is the bottleneck? Are you with me here? The first question is memory the bottleneck, or is it the the compute the bottleneck? Because if even a single core can perform 25 gigaflops per second, but the operational intensity in this particular case is so low that you are not able to improve the, that you are not able to saturate the computation. You are not able to saturate the computation. So if you see, we want to improve this thing. Okay, we want to, so this peak, this is what I have highlighted here. So this is what we would like to improve. Peak compute throughput is, in order to improve the peak compute throughput, there are two ways of doing it. One way of doing it is increasing the operational intensity of the problem. But the operational intensity of the problem is a function of the program. Okay, you may not have much leverage there, right? But if you look at the memory bandwidth is a function of the system hardware, and there also you don't have much leverage, right? Yes or no? So we are stuck there. On one side, operational intensity is a property of the program, and on the other side, memory bandwidth is a property of the system. So how do we go about improving the peak compute throughput of the system? That's the challenge that is there before us. So one way of doing it is, while we cannot increase the memory bandwidth, we can increase the effective memory bandwidth. How can we increase effective memory bandwidth? Yeah, so we have to use cache memory. By using the cache memory, if we can load the data and keep it in cache, we will be able to increase the effective memory bandwidth. So this is a very important observation. So, improve or increase effective memory bandwidth. Effective memory bandwidth. How do we do it? By using caches. So now comes the next question. Just because we have the cache, is it possible for us to use the cache? What does utilization of the cache, does it in some way depend on the program? Right? So what are the properties of what properties the program should have to be able to use the cache well? Sorry? It should be? The accesses should be in a local region. Okay? So we want to exploit in order to be able to use the cache as well. So programs should exhibit a property, locality of reference property. Locality of reference. And when we talk about locality of reference, there are two kinds of locality of reference that we talk about. One is temporal locality of reference, other is spatial locality of reference. Temporal and spatial locality of reference. So in the problem that we are looking at, where y is equal to alpha x plus y, so if you go ahead and look at the computation, only alpha shows temporal locality of reference. You use alpha again and again across the time. But if you look at the vectors, no, alpha y is equal to x plus y, they don't show any temporal locality of reference because you are accessing all the elements only once. Okay, x of 1, x of 2, x of 3, y of 1, y of 2, y of 3. But what is acting in favor, although no, they don't show temporal locality of reference, they show spatial locality of reference. That is, when you access x of I, you end up accessing x of I plus 1, x of I plus 2, x of I plus 3. So the vectors x, so these vectors x, y, and z, so there is no z here, they show spatial locality. And alpha shows temporal locality. So not only they show spatial locality, all these references, they are stride one references. Stride one is they are accessing, these elements are accessed one after another. Okay. So as a consequence of this stride one accesses, number one, and that we are, so what happens is the number of cache misses will be less. Why? If you remember from your CS4 course, when you fetch a block of data from the memory, you just don't fetch 4 bytes of data. You fetch 32 bytes or 64 bytes, which is the size of the cache line. So what happens is, if you think that if your cache line size is 64 bytes, then when you access the first element in the cache line, then what happens is you will get a miss, but the rest of the 7 accesses, assuming that we are accessing floating point numbers, each cache line can hold 8 floating point numbers. So there will be 1 miss and 7 hits. Okay, that is how spatial locality of reference works. But if it's a stride 8 access, what happens? Then everything is a miss, because you access A of 0, you are accessing A of 8, but so you're not accessing A of 1 to A of 7. So every time you access A of 8, A of 16, every time it becomes a miss. So usually what happens is when the stride increases, it will have an impact on the locality and our ability to utilize the cache. This will have an impact when you work on BLAS level 2 and level 3 programs, where you try to do matrix vector operations and no matrix operations. What happens, in C, if in C, when you access the elements of a matrix row wise, it's a stride 1 access. But if you access the elements of the matrix on a column wise, it's no longer a stride 1 access, it is a stride n access where n is the size of the. Okay, so this is what happens. Well, we will revisit these ideas again, but one thing though is, if it is stride 1 access, it is really good for us. Okay, even if it is not stride 1 access, even if it's a stride k access where k is the regular stride, the compiler and the processor still tries to do some kind of optimization by doing prefetching. So when we think of data prefetching, so there are two kinds of data prefetching. One is hardware prefetching and other is software prefetching. In the hardware prefetching processor, what it looks at is it observes the memory access patterns and it realizes that the program is accessing every 16th byte and it automatically prefetches the next 16th byte. Okay, this is what is called as a hardware prefetching. In software prefetching, the compiler explicitly inserts prefetch instructions in order to get the data well in advance by the time that particular data item is accessed. So this is some kind of peek into the impact of memory and especially spatial and temporal locality properties of the program on our ability to utilize caches. And if you are able to utilize our cache properly, then our effective memory bandwidth increases. And if the effective memory bandwidth increases, the peak compute throughput increases. Okay, so we will again revisit this spatial and temporal locality again, but this is a kind of peek into what happens under. Okay. So are you all with me here so far? Okay, so now let's look at this program. Let's go here. Yeah. Control. Okay. So this is the program that we were looking at, AXPY program. Let's try to open this. What's happening here? Table access. Okay, finally. Okay, my program code is there. Huh? Okay, let me do one thing. Next time I will use Git for this time. forgot that I have a lot of stuff there. Including, sorry, let's do it. Great. So this is the simple code, Control Shift plus, that so this takes as this we are computing y is equal to alpha x plus y. The signature for the signature that I have posted in the homework problem is a bit more complicated than the signature because it will be used for several other purposes. Because of it, that signature is different. But here it is very simple. So here what we are doing is so we are passing the vectors x and y, and n is the dimension of the array, the number of elements in these arrays, and a is the scalar which we would like to multiply. And then there is a driver program, and so here in the driver there is this random. I am initializing this these two vectors x and y, and the default dimension vector length is 1 million, 1 million elements. And so we are allocating memory for these elements from the heap, and then here we are taking a snapshot of the time, and we are calling this AXPY function here, and then again we are taking a snapshot of the time, and we are, so here we know theoretically the number of gigaflops are there. There are 2n operations, 2n into 10 power 9 minus 9 to indicate though we want to compute the gigaflops, the number of giga operations. Okay, so 10 power 9 operations is 1 gig, so we are dividing it by 10 power 9. That's what we are doing here. Divided by, on line number 40, we are doing it the total number of gigaflops divided by time. Calculate. So this is how we are doing it. Let's take a look at the make file and helper.c. Yeah, so this is the code for tick and talk and random vector. So this is the code. So and then there is helper.h where all the header files signatures are present. Helper.c and then make file. So this is our make file. So the compiler that we are using is GCC ICC compiler, and using -03 option. And right now, if you see, this is not, we are not using any optimizations or anything. No, we are not doing any parallelizations or anything. So everything is common. This is the baseline code that we have. So now let's go here and try to do the computation. So make -b, and I would like to use to start with GCC. Okay, so make -b cc. I'm overriding the default ICC compiler that is present there, and the flags C flags. C flags is equal to -00. So if you don't enable any optimizations, let's see what is the performance that we get. So we are getting 1 gigaflop per second. If I use -00 optimization option. Remember what is the peak compute power for one core? It is 25, right? 25 gigaflops is per second is the peak compute. Let's see. So if you use minus O1 option, does anyone know the option to use for GCC to generate the optimization report, all the things that it did? Maybe verbose will do. Minus C flags minus verbose. I forgot that option. I should have checked it. Yeah, I don't think this is giving all the story. Okay. So let's leave it like this. So we are getting, if you do this one, so dot AXPY. So we are able to get up to let's say 4 gigaflops by using minus O1 compiler optimization option. Let's say if you use minus O2, let's see what we get. And we use minus O2 is not really helping out. We are still about the same. And minus, let's try O3. See, the number of gigaflops went up to 8.5. And you know, now if you want to analyze what is going on when we use minus O3 option, you know, minus help is equal to optimizers. Balaram Krishna said. Let me use this here. Make GCC OPT report minus O3 minus help is equal to optimizers. Awesome. Thank you, Balaram. Thank you. Thank you. More AXPY.opt RPT. This is Intel. I changed the compiler, right? Why still it is getting GCC? Oh, dumb. I'm changing it in my local machine, but okay, good. Insert minus. Insert minus O3 minus help equal to optimizers. RM star.opt. No, this is only telling us all the printing all the optimizations that we can bring. Okay, this is not helping actually. Okay, just leave it like this. Okay. So here, can you tell me, so a couple of ways to understand what is happening under the hood? Is there a way to understand what is happening under the hood here? What can we do? There is one tool that we have used, and this is not consistent. But you know, one time if you are able to get that peak thing, that whatever that 8.3, that's a representative, because no, the performance usually depends on what are all other loads that are present. So there will be some variance. So, but at least we can say the peak that we are able to get is 8.2 or 8.3 up to 9 gigaflops per second. And then still we have to reach 25 gigaflops per second using just one core. That's the goal. Okay. What else is something I'm yeah. So this is the question. So how can we understand what is happening underneath? Okay, is there any tool that we can recall which can help us tell what is happening underneath? This why we are able to get why we are able to move from 1 gigaflop per second to 9 gigaflops per second. Is there any tool which can help us understand this? Do you recall the pin tool? What does the pin tool? So the pin tool, it does dynamic binary instrumentation. It can do, using that we can do variety of analysis, but one particular analysis that we did, very simple analysis that we did using pin tool is, it tells us the number of different instructions that are executed. Okay. So like for example, our processor, the processor on my system, it has a vector instruction set. And if you analyze using the pin tool, earlier the vector instruction may not be executed at all, but then after the optimization, the vector instructions might have been executed. Okay, and the pin will profile your program and tell, hey, you know what, you are started using these vector instructions, and then we will be able to say, hey, because of these vector instructions, we are able to get the performance. So that is one approach. The other approach, of course, is GCC minus O3 minus G minus S, whatever this AXPY.C. And if you see AXPY.S, go to main, or there is no main. And then you can see here, the code here, there is, you can see the code here. You can see that we are, this PS stands for single precision. So we are using XMM1 register, XMM3 registers, the registers that you are seeing here, XMM3 register. And then there is an add instruction here. And then there is a multiply instruction, and then there's an add instruction. All these instructions, and then you can also see there is an add Q16RAX. All these instructions tell us that the compiler generated code, and this code is using the SIMD lanes in the processor. Okay, so the SIMD lanes, we will discuss them in detail, perhaps maybe in next class. But broadly speaking, it is possible for us, like for example, if you want to add A of 0 plus B of 0, A of 1, B of 1, A of 2 plus B of 2. So if you see so on and so forth, so this is the computation that we are doing, A of 100 plus B of 100. So if you just use the scalar instructions that you have learned in your CSO course, these additions will happen 1 clock cycle at a time. So approximately this may require some 100 clock cycles. But the vector instructions, they can do 4 additions in a clock cycle. Okay, vector instructions. So because of this, what will happen is, we might be able to execute the same using 25 clock cycles. Okay. Are you with me here? Good. So now let's try to do more simple stuff. So the reason why GCC -03 option is able to give us such good performance, there is a 9x performance improvement. We went from 1 gigaflops per second to 9 gigaflops per second. So there is a 9x improvement in the performance. We are able to get it primarily because of the vector instructions. All right. So now let's go back. Now let's try to see what we can achieve using Intel compilers. Or before we go for Intel, we can try to use the LLVM compiler, which uses Clang, and LLVM also may give similar performance as C flags -O0, Clang -B, Clang not available. It's there. Okay. Yeah. O3 optimizations. What is the relationship between O3 and call grain? Call grain also does that. Well, perhaps it is possible. The only challenge there is call grain is an interpreter, so it just takes time. I think it should be possible. Yeah. Okay. Instruction level split also it shows call grain. Okay, I see. It is quite possible for call grain because it's an interpreter, because its base call grain is based on Valgrind. Since Valgrind is an interpreter, so it is possible for it to capture everything and do. And yeah, the only small challenge, and it could become bigger challenge, is there are two challenges there. One is because of the interpretation, you don't get accurate gigaflops, but you will still be able to get like which instructions are being executed more frequently. Okay. So Clang LLVM compiler, it is taking this is so Clang with -01, it is able to get 3.8 gigaflops. Let's see what we have. 7 gigaflops, 8 point. So usually in many cases, Clang, which is LLVM compiler infrastructure, and the GCC compiler, they give similar performance. Okay. Now let's try out ICC compiler. ICC is very, very powerful compiler, and Intel C compiler. ICC is Intel C. So 1 gigaflop with -01, it is giving 4.48. So if you see all these compilers, be it Intel compiler or GCC or ICC, they are able to get some 9 gigaflops per second. Beyond that, they are not able to get any improvement. Yes or no? That's what it is looking like. And if you see where we are, this is where we are, and So you can see here that the operational intensity is 0.5 and memory bandwidth is 41.6, and the peak compute throughput that is available is 10.4. So we are close, right? Because the memory, the achievable memory bandwidth, if you recall from the last class, when we use the stream benchmark, we are not able to get this 41. This we are not able to get it. What we are able to get, if I recall, is something around 30 is what we are able to get. 30 or that also with very fancy options, ICC options, we are able to get. So now if that's the case, then yeah, so it is even just 7.5 it is showing. So maybe no, yeah, so we are around the ballpark. So what I would want you to impress upon you is that we are able to get this thing even before running the program, that approximately this is the max that we might be able to achieve. Okay. And here, do you think is there any possibility for us to improve the performance further? Is there any possibility for us to improve the performance further? Can we improve the operational intensity? No. Can we improve the memory bandwidth? No. Why? Because there is no temporal locality in this program, so we have to rely on spatial locality only. Okay. So let's see what other things we can do to see if we can get a better performance. Let's try out a few things. Also, let's do one more option also. Let's see Intel minus X host. If it has any. We are able to hit 10 sometime. This minus X host, it will, what it does is it tries to optimize the code generation for the particular machine on which the compilation is being. Okay, like for example, the whole compiler, it looks at here, this is the processor, this is the SIMD lanes that are available, and it uses that particular processor and the system to get the best performance. And if you disable vectorization explicitly and see whether we will be able to get the same kind of performance. Okay, so let's say if I say minus novec, again I will have to make file, maybe licensing. No vectorization. So when we disable it, when we disable vectorization, 4.8 is the maximum gigaflops we are able to get. But let's say if we enable vectorization, so broadly, what I would like to point to you here is when we enabled vectorization, we are able to get approximately 2x speed. Yes or no? 4 gigaflops per second approximately without when we disabled vectorization, and when we enabled vectorization, we are able to hit 8 gigaflops. And when we use the option minus X host, which kind of no, the compiler just focuses its attention on generating code which can just run on this machine. then it is able to get up to 10 gigaflops. Well, I think it depends on the other workload on the system. That's a good point. If you want to get more stable thing, that's the reason why we take lots of runs when we are reporting numbers, like we take lots of runs, and the data size also we need to increase in order to see what's going on. You have a point there. I am not exactly sure. In order to reduce this variance to some extent, maybe, like for example, if you go to AXPY.c on this one, driver.c, and let's say if I put one more zero, if it makes any sense. ICC. So now it's interesting. We are more or less getting 5 only when we increased it. Interesting. Should we put no wake and see what is happening? So it is showing consistently 3.8. With vectorization, we are able to go up till. So what's the speed up that we get? 3 point something and 5 point something. So some 20% improvement, 30% improvement, we are able to get. That's all. Okay. Yeah, that's true. Why did it reduce when the size of the data? Because there itself, it is looking kind of some noisy noise. Because the way we are taking snapshots of the time, because if I'm right, when you take this time tick and talk, when your process is scheduled out and scheduled in, the time is also included, I guess. Because we are taking a timestamp wall clock time, right? So interferences from other process, if your process itself is a small process, the interferences will add more to the noise. But if you are running it for a longer time, the noise added because of context switches may get reduced out. But then there is a counter argument: as the time increases, the number of context switches also increase. So my argument is. But that's true. But here there is no temporal locality. It's all spatial locality. No?
What if like in the previous one, what happens is like it's only a 1 MB data, right? So when we first run it, there are a lot of caches. When the whole data is stored in the cache, that when we run it again, it runs faster because everything is.
I am not sure. Primarily because when there is no temporal locality, it doesn't make sense because the data is there, it's there. Okay, you're not using it again. Hmm. Hmm. Okay. Do you mean that performance could depend on whether it's an aligned load or unaligned? See, what definitely happens is if it's an unaligned load, the memory bandwidth goes down. Okay, because of that, the performance decreases. But whether that is the cause or not, I'm not sure. Where should I keep? Also, meanwhile, I'll also try this thing, GCC. What is the other thing? Minus C flags. C flags is equal to minus MR equal to negative. How do I pass to make both with a space separated thing? This is not working. I want to say, this is what. 5.38 is the peak. Okay, so let's try one more. Minus M AVX 2. ICC. We'll talk more about the details of vectorization in the next class. I'm just trying to get a feel for so approximately we are saturating at 5.4 gigaflops per second. Okay, and if you think about it, how much percentage of CPU we are able to use peak flops? Out of 150, we are able to use 5 gigaflops. It's just a shame. No? We are not even using 5% of the peak compute power. Okay, so what's the point in buying a 2 lakh machine and you're using no, just 5% of the peak compute power? Let's do one small exercise so we can control this. This is on this particular machine. I don't know what is the peak compute power that is available. Make is also not. GCC is also not. Okay. so, okay. So now, yeah. Well, what's the next thing I want to see? Oh, yeah, this is what I would like to see. So VI makefile, it's not makefile, VI AXPY.c. So here, these two, but all since the compiler, so when we look at vectorization using pragmas, etc., in the next class, but here we are telling the compiler, so please vectorize the following loop for sure. That's what we are telling here, and let's do this and see what happens. Okay. So since the compiler already auto-vectorized, this particular pragma doesn't have any effect. Are you with me here? So this particular pragma, it doesn't have much of an effect because the compiler has already vectorized it. But this one we can try to use. This uses all the cores that are available on the system. So this is OpenMP pragma, which tells us parallelize the following loop. So like, for example, if there are million iterations in the loop and if there are 4 cores on the system, then what happens is 1/4 of the number of iterations are scheduled on each of the cores that are available on the system. So you can expect 4 times the performance improvement, approximate. On my system, there I have 6 cores, maybe 6x performance might be possible. I don't know. Let's see. Hash pragma OpenMP. This should be possible, but I don't know. Unrecognized OpenMP pragma. Cannot be the case. Let's see. Can someone tell me the OpenMP pragma for parallelization? It worked when it tried out. Now we should get some vi AXPY.c. After this, we will stop. This should work. I'm not sure what is happening. Why Intel is saying, Intel compiler is saying it's not able to recognize this pragma. I tried it out. Sorry. We need a for because that will tell. Yeah, this should work actually. There is no reason why it shouldn't work. So what this tells is that specification that pragma tells the ICC compiler or any compiler for that matter to parallelize the following loop so that all the cores are used. But we are not getting it is saying the pragma is not recognized, which is bit okay. Let's do one thing. Edit makefile. Do we need to compile it using any special OpenMP flag? Can someone check what's the flag to use? -f OpenMP. I think we may have to. At least GCC uses. Yeah, I think so. OpenMP. Now it is able to compile. So we have to use that -f OpenMP. Let's see what happens. We got anti-climax. Welcome to Programming for Performance course. is not followed by a parallelizable. Okay, so food for thought. So we will try to, so these are the challenges that we face. So what we are trying to get here is, so through vectorization, we are able to get some 20 to 30% improvement in performance, like from 3.5 gigaflops per second, we are able to get 5 gigaflops per second. Ideally, we would like to go till 6 or 7. And the peak achievable floating point performance is, using roofline analysis is 7 gigaflops per second. We are falling quite short of it. And if you use all the cores, we are hoping at least we will get 4 to 5x improvement from the baseline performance, but we are still not at there. So yeah, so we will see how to work on this and how to improve this in the next course. Okay. Yeah.
Already parallelizing the standardizing the code. Why are we accepting
Because O3, so yeah, it's a very good question. When we use minus O3, the compiler tries to auto-vectorize the code. But what happens is, I will conclude this with a very important observation. Why there are a couple of ways of, there are 2-3 ways of doing this vectorization. First one is relying on the compiler to do auto-vectorization, compiler-based approach. The second one is the pragma-based approach. Okay. So the compiler, if the based on compiler analysis, let's say the vector, so vector X and vector Y, they can overlap in memory. Compiler doesn't know any information why they shouldn't be overlapping in the memory. It's quite possible, right? You can send 2 vectors as parameters to the function, and those 2 vectors, they can have overlapping memory references. So then what happens is, if you go ahead and vectorize the code, then the semantics of the code changes. Okay. So the compiler will do a conservative analysis. Here, I don't have information that these 2 vectors may or may not overlap. I cannot conclusively say that they don't overlap. So let me avoid parallelizing this, vectorizing this. But when you give this pragma, you are telling the compiler, don't worry, I take the responsibility that these 2 doesn't overlap, and please go ahead and vectorize. Okay. So this is very, very important, because when compiler does program analysis, it has to assume the worst possible thing that can happen, and that will prevent a lot of optimizations to be enabled. So, but through pragmas, you give hints to the compiler, don't worry about it, it's all right, it doesn't happen. No, if it happens, the responsibility is on me. So that kind of assurance, if you give the compiler, then the compiler will use that information and does program transformation automatically for you. Okay, so these are the 2 approaches that we have seen. We didn't, so one is, we didn't look at the second approach. One is compiler based approach, compiler driven approach. Second is pragmas. And the third is, by using what are called as intrinsics. This is what we will see in next class. And yeah, so This is not a good way to go about doing, because this code is not portable and it's very, very challenging to write code using intrinsics and lots of issues. So by and large, we try to use pragmas and or some other frameworks to see, to achieve the end goal. Okay, so that's all for today. We'll stop here and we'll catch up in the next class. Yeah, let's try to do it this way. I think there are some little bit of hiccups, but I think it's good to kind of discuss this face to face and figure things out.